Welcome to Designing Clever Linkages and Cams. My name is Orion DeYoe. I'm the Senior Manager of Mechanical Engineering at First. Formerly, I was the Mechanical Engineering Manager at Robotics. I'm an FRC alum, an FTC and FRC mentor. I've mentored a few different teams, but most recently I was the design lead for FRC Team 3005, the Robochargers, as well as their FTC teams. We've got a few goals for this presentation. I want to, in no particular order, provide some guidelines in terms of when linkages and cams are useful in kind of the current state of both FTC and FRC. I want to provide some tips and tricks for building intuition for linkage geometry. Originally, this presentation was quite a bit longer and had a lot more information about cams in it, but it got very long very quickly. There's already a lot of slides here, so we're going to be focusing mostly on linkages when we get into the details. And so then we're going to be building kind of a starting toolbox of just some examples of different types of linkages and what you could use them for. Kind of a quick outline for the order of events. We're going to just talk about what linkages and cams are, really high level basic stuff. We're going to talk about where they can be useful in first competitions. We're going to talk about the reasons when you would choose to use a linkage or a cam as opposed to some other method of transferring power. We'll talk about some more details about different types of linkages that are available. We're going to run through some kind of really quick shortcuts and kind of like tricks or other ways of thinking about linkage geometry. And then we'll finish off with some examples from some recent 3005 robots. And we'll have some time for questions at the end. All right, so we're going to start off by talking about what are linkages and cams. Linkages are a system of rigid bodies called links, and they're connected together through rotational joints. There's some examples here on the screen of some different types. We'll go into a little bit more detail later, but the key thing is you have these, rigid pieces, and they have rotating joints kind of at their ends. They can have different numbers of links, and each of the links can be different sizes, and we'll talk about what those variations look like. Cams are a moving surface that a driven body called a follower reacts against to produce some motion that you want. The key thing here is that the cam is the driving part and the follower is the driven part. Probably the typical example of a cam that you've seen is this one here on the top left. That is kind of like a basic cam example that you will see all over the place. And it kind of creates the impression that the cam kind of has all of the complicated, specially formed geometry, and the follower is just a very simple device that follows it. That's not always true, and we'll see some examples right at the end of this presentation of what that might look like. And so it's just kind of important when you actually get into cam design to kind of get rid of that assumption that all of the hard geometry has to live in the cam instead of the follower. All right, so we're going to talk about where these might be useful on first robots. So at a high level, linkages and cams are a method of power transmission, right? You can think of them in the same way that you think about gears or belts or chain or any other power transmission method. And so they're used for the same things, right? They're used for moving power from one place to another. They're used for transforming motion in terms of gaining a mechanical advantage and increasing speed or displacement and decreasing force or vice versa. And then you can also use them for converting between linear and rotary motion. Linkages and cams are also good for producing more complicated motion. Generally speaking, if you're just doing something that's just a pure linear motion or a pure rotary motion, you don't necessarily need to use a linkage or a cam. especially if you don't need to relocate that motion. But if you have something that's a much more complicated motion, like you can see this intake deploy on this 3005 robot here, where it's kind of doing a translation and a rotation at the same time. Um, that's much harder to do with any other power transmission method. Um, and this could be useful for, tight packaging, which is a pretty common thing that you need to do on these robots. Um, Sometimes you have multiple degrees of freedom that you want to move in some synchronized way. Um, and linkages and cams can let you do that. We've got a couple examples here. We've got this 2015 robot where this end effector on this robot is attached to the end of the arm through a linkage, and so when the main joint of the arm moves, the end effector of the arm stays at a constant orientation relative to the floor, and they're able to keep these totes level. This animation is not working properly for some reason, but take my word for it, I guess. And there's other uses for this. Sometimes you can use a linkage or a cam to produce multiple functions off of a single, motor gearbox, and we'll talk about that a little bit more later. And then there's some more novel functions that you can use linkages and cams for. You can use them to lock a mechanism to not be back drivable. You can create motion that's intermittent. You can create motion that has some dramatic motion profile for like launching, or there's an example of this like snail drop cam for this kicking mechanism on this 148 robot over here. And there's a lot of potential other applications in that same vein. So we're going to talk about some reasons why you would choose to use a linkage over or a cam as opposed to some other method of power transmission or some other method of producing some complicated motion. A big one is geometry or packaging, right? Like you've got space constraints on your robot, and sometimes some specially customized linkage geometry or cam geometry is really the only way to get your robot to move from, or some mechanism on your robot to move from one place to the other within the space constraints that you have. That can mean having a mechanism that has some extension that folds up into a much smaller or weirdly shaped volume, or it can mean taking the driving components like the motor and gearbox and moving it to another part of the robot where there's more space, and then just using a linkage or something to move that power to where you need it. There's some performance reasons why you might choose them over another method. A big one is mass distribution, where you may want to take the driving component, motor gearbox, and move it off of the main part of the mechanism to kind of maybe reduce your center of gravity or remove weight from a mechanism that needs to move quickly. When you're talking about producing some very complicated motion, if you don't use a linkage or a cam, you may need to use like multiple motors to produce multiple degrees of freedom, whereas a linkage, for example, can produce that motion using only a single actuator, and so that means that you can save a motor, controller, gearbox, which can save weight. You can also sometimes make linkages and cams, especially linkages, lighter than an alternative power transmission method, like using a sprocket and chain, for example, will typically be lighter than a high performance, or will be typically heavier than a high performance linkage. And then linkages especially also give you the ability to control stiffness. If you need something really stiff, like a 4-bar arm, you can use carbon fiber or other very stiff materials and build a linkage that's much stiffer than another power transmission method. Or if on the other side of things, if you need a mechanism that's very compliant and flexible, like this intake here on the top of the screen, then you can build in that flexibility that wouldn't typically be possible with like a belt or a chain or gears. So here's some kind of like logistical kind of considerations here. Um, a lot of times you can save a motor or gearbox, like I mentioned, with a linkage or a cam, and that can save you money. Um, in terms of reliability, you can have less moving parts or less parts that are rubbing on each other potentially. You won't have maybe as many electronics, or you won't be putting electronics on the things that are moving because you're able to move power off of those mechanisms, and that can improve your reliability overall. And then in addition, when you're talking about adding mechanisms or functions to a robot that already exists, um, linkages and cams can make that possible through a variety of different things. I wanted to quickly talk about some reasons that I maybe myths or like reasons that I don't think are valid and I think lead people down a wrong way of thinking about using linkages and cams. Um, the key thing here is that at a high level, linkages and cams are not inherently simpler than using a motor, a controller, or a gearbox. And we'll talk about that on the next slide in a second. Um, they're still, pretty high part count, you know, high complexity power transmission components. You have to do as much or more engineering on a linkage or a cam than you do for sprocket or chain or anything else. Like they are not simpler, and if you're a beginner to it, they aren't necessarily going to be more successful. The one asterisk here is that when you're talking about especially like following or dependent motion or complicated motion, if your team's strong suit isn't software, you can use linkages or cams to kind of shift the engineering workload from the software side to the mechanical side, and so that can be a useful situation. Um, the continuing on that same theme, like when we're talking about producing complicated motion or producing a lot of different degrees of freedom, the reality of modern FRC and FTC is that fast, tight, closed loop motion control is pretty easy and approachable even for beginners. There's a lot of really good power transmission components available off the shelf in terms of motors, gearboxes, gears, shafts, bearings, sprockets, pulleys, anything you could want, you can get those off the shelf, and so they don't require a ton of custom manufacturing or design to work with. Um, Linkages and cams, especially, they rely on very customized geometry that's specific to your application. And so if you need to be really agile and flexible and iterate quickly with your robot, linkages and cams are not necessarily the best way to do that, because once you've built them, they're kind of locked in place and you have to kind of throw the whole thing away and start over in a lot of situations to make small adjustments. Whereas if you are putting motors on different degrees of freedom on your robot, you can just adjust positions in code and things like that. And so it's important not to kind of get too stuck in this linkage and cam thing, because it's not necessarily what's going to help you be competitive on the field in every case. FRC especially is limited on time, and so it's all about logistics, right? It's spend your time wisely, only on things that are a value add for you. Spend your resources on what actually makes a difference on the field. And there may be very fun or educational aspects to designing more complicated mechanical components, but building this like complicated or elegant machine doesn't necessarily help you win matches. And so as long as you're evaluating that realistically, you'll be happier. All right, so we're going to talk about some more specific information about linkages here. We're talking about the parts of a linkage. So we mentioned the links and the pivoting joints. I'm kind of trying to use these examples in a lot of my little images and animations throughout the slide, and I tried to kind of color code them where the fixed link is kind of like the link that doesn't move as the kind of the reference point of the linkage. And I've color coded most of those blue. And then all of the other links are moving in some way. One of them is the driving link, which is generally attached to like a motor and a gearbox or an air cylinder or something like that, whatever actuator you have. And then one of the other links in the system is going to be attached to the thing that you're trying to drive, right? And I'm calling that the driven link. And then in links that have more than 3 links, you also have an additional link called the passive link that's just kind of there to constrain the geometry of the system. You customize a linkage by adjusting the lengths of each of these links and how many there are. So to start off here, a 3-bar linkage is kind of what it sounds like. It's a linkage with 3 bars or 3 links. Those links are connected together to form a triangle. Now, in order to make this move, one of the sides of the triangle has to change length. And because that side of that triangle is changing in length, you kind of have a linear motion there on that one side of that triangle. And so 3-bar linkages are really useful for converting between rotary and linear motion. They also have some additional kind of slightly more advanced functions in terms of over-centering. We'll talk about a little bit about that, but that's mostly out of scope for this talk. And then continuing on from a 3-bar linkage, the other and probably the most common type of linkage is a 4-bar linkage. I have several different examples here on the screen with some different kind of classes. And these classes of linkages they're classified by the relative lengths of the different links and their kind of configuration. The first one here on the left is just called an equal 4-bar, and the key thing here is that opposite pairs of links are the same length. Not necessarily all 4 are the same length, but opposite pairs are. And then this group in the middle column, unequal, is just where they're not. It's just not equal. At least one pair of links is a different length, or all 4 are different lengths. And the unequal produces a much more complicated motion. Equal kind of is a parallelogram and always stays in a constant orientation. And then we've also got this crossed, which can be useful but is not nearly as common. Linkages can operate in 2 different modes depending on their geometry. You can have the driving link kind of just continuously rotate. That's a lot more common in like older industrial equipment where you don't have a motor that has good position control and you want to create an oscillating motion. That's not nearly as common anymore, and it's not as common on It's not common on robots particularly at all. And then, so a lot of the linkages that you will use on a robot are going to be what's called a reciprocating linkage, and this is where you're kind of just doing a position control on the driving link, and it only operates within a certain range. Because of just the way the linkage geometry works, there are some linkages that cannot continuously rotate, or at least not continuously rotate in a useful way, whereas basically all linkages have some range that they can reciprocate within. And then going further with this, you can take multiple linkages and connect them together, and you can do this to produce more complicated motion or to change the mechanical advantage of your system. A lot of times you'll use a compound linkage to drive a larger 4-bar linkage with some other linkage. There's an example here of this intake where you've got a 3-bar linkage that's formed by the air cylinder, and that linkage is connected into what we call this compound link, which is basically just a link that shares a connection with the other linkage. And so basically you can identify a compound link by looking at how many pivot points it has, like how many joints it has. And if it's got 3 or more, then you know that that's a compound link. And generally speaking, like that compound link is the driving link for one linkage and the driven linkage, or the driven link for the other linkage. Talking about a little bit more of an advanced concept here. But it's really important. It's really important to kind of like believe what's on this slide, because this is one of the things I see trip up new designers a lot. Do not get stuck on the orientation of your linkage, right? Like linkages don't always have to be this like perfectly horizontal thing that relative to whatever you're driving, right? I have this thing that there's not really a good term for it, but I call them handles, which is this, when you're looking at this yellow part here over on the right, I can take this linkage that's driving this mechanism, and I can reclock it in any orientation by just adding this little kind of lever on the end of the mechanism. And this is something that I see beginner designers just not do at all. They get really stuck on, the kind of shape of their mechanism and the connection point to the linkage. And so you could always do this. You can at any arbitrary angle you want. And then kind of a very related concept is this thing called a bell crank. This is a very, very common term. And a bell crank is this kind of compound link that, takes a driven force from one direction and redirects it into another angle. I want to talk about this thing called indeterminism or a linkage becoming indeterminate. This is not a particularly widely accepted term, but I hear it used a lot in robotics, and so I'm using it here. Basically, this kind of goes back to reciprocating links and the fact that reciprocating linkages kind of can have geometry where they only operate within a certain range in a useful way. And so if we look at the linkage here on the top, you've got the driven link is the green one, the fixed one is the blue one as usual. The yellow and the red links are in a straight line. And so if you then try to push in the direction of this white arrow here, it's not defined. It's indeterminate what direction the red and the yellow the links are going to go. And so this is a condition that you typically want to avoid at all costs. The key thing here, though, is that the driven and passive links are the ones that are in line, and the driving link is not in line with any of the other links. We'll talk about an example of where that other case would be useful. All right, so we're going to go through some really quick linkage shortcuts here. So these are not necessarily all going to be useful, and the purpose of this section is I have struggled to teach kind of linkage design for a long time, and I've met with mixed success. And so I'm kind of using this presentation as a little bit of a test run. And so I'm kind of trying a bunch of different ways to show linkages and kind of explain them. And what I'm hoping is there's a few things in this presentation that made something click for you. So if this is something that you have struggled to design and there's something in this presentation that you're like, oh, that makes sense, especially in this kind of little shortcut section here, please let me know, because I would like to try to improve the way that I teach this topic. So the first thing here is called the skeleton. The kind of wireframe skeleton of a linkage is the only thing that matters for its behavior. You treat the pivot points as points or vertices, and you connect those pivot joints together with lines, and you kind of just evaluate the way that polygon moves. The key thing that this brings into effect is the physical shape of the link doesn't matter. The only thing that matters is the distance between the two pivot points. So this is particularly useful when you're trying to make linkages that have to fold around other components. Like you can kind of see some weird shapes on this linkage on this intake up here. This is also useful when you're designing in CAD at the early part of the design phase, because you can just kind of sketch a bunch of lines and figure out your linkage geometry without knowing anything about the rest of the mechanical system. Adding on to that, thinking about links as circles is pretty useful, right? Because the links that are attached to the fixed link, they're just pivoting around one end, right? And that's the only thing that they're doing. And so the other end point of the link traces out this circular arc. And sometimes when you're thinking about linkage geometry, not even thinking about the link as a line and just thinking about the link as a circle, and just knowing that the endpoint can be anywhere on that circle can be useful for kind of building intuition about how the linkage will move. Again, this is useful when you're doing early season sketches to figure out your geometry, where you can kind of just sketch in a circle and not worry about what the angle of that line is. When you're designing linkages, you really only care about the two extreme end positions in the vast majority of cases. Trying to do design work with defining the geometry of a linkage in kind of the middle of its reciprocating motion generally is harder than caring about what does this linkage look like at this end, and what does the linkage look like at this end. Generally speaking, when you're talking about early season CAD and you're doing sketches again, uh, what designing for the extremes looks like is you're just drawing the linkage in two different positions, the fully extended and the fully retracted position, for example, and you're kind of just ignoring the motion in between. And then even if you don't, you know, explicitly design that intermediate motion, you could still use that motion, on your robot by, doing position control with motors or whatever. I also find it very useful to imagine, certain linkages as linear actuators, especially three-bar linkages. If we think about a linear actuator like this air cylinder that I have here on the screen, small arc segments can be kind of approximated as a straight line, right? And so when you're thinking about, the linkage geometry that you need on your robot, thinking with all of these kind of arcs and circles can sometimes be more difficult. But if you just think about the two extremes and of the linkage, and you think about it, the end point of that linkage, right, the joint of that linkage just going in a straight line from the starting point to the end point, that can be a much more intuitive way to think about it. And you can see that, like this animation with this air cylinder here, with this link behind it, you can see that the error in terms of like position between what the air cylinder is doing and what the linkage is doing is actually pretty small, and it can be ignored in most cases. And then even when you have a larger range of motion, like this continuously operating three bar here, you can kind of just think of the two extremes of that continuous rotation, and you can still think of it as a linear actuator, even though it does do a much more dramatic motion in the other direction. You can kind of ignore that in a lot of cases. Something that's useful for visualizing unequal four bars, where this whole shape is kind of weird. It's very difficult to have an intuition for the way that an unequal four bar will move. And so one trick that you can think about with these unequal four bars is, generally speaking, you'll have mechanisms where the driven link, which is this red line in this image here, is opposite of the fixed link, which is the blue line, and so the driving link is adjacent to both of them, and that'll be controlled by a motor, an air cylinder, or something else, and then the passive link is kind of just there to constrain the geometry. And so sometimes when you're trying to figure out, hey, I kind of know what motion I want, but I don't know what linkage geometry I need to produce that motion, sometimes it's useful to think about this system without the passive link at all, and just think about having a motor at this point marked arm joint 1 on this image, and have another motor on arm joint 2, and just think about, like, what if I used software to just like control these independently? How would I produce the motion that I wanted to produce? And then using that to kind of, build an idea of the motion that you're trying to create, and that can make it easier to then figure out linkage geometry later. Linkages are kind of like logic gates. If you're familiar with like the computer science concept of like AND gates, OR gates, NOT gates, etc. And kind of the concept here is like you've got inputs, one or more inputs, and you've got one or more outputs, and you can kind of connect these gates together to produce some output, which in our case would be some mechanical motion. And linkages kind of work the same way, and you can kind of think about compound linkages as these kind of like logic gates that you have in your toolbox, and you can kind of connect them together in different ways. It's usually helpful to just think about each of these kind of atomic linkages as their own thing, rather than trying to think of the whole complicated system at once. I'm calling this, 4 equals 3 plus 3. In a lot of cases, it can be useful to think about a 4-bar linkage as 2 3-bar linkages combined. And so this is useful in the opposite case of the 2-joint arm case, where the driven link that I care about in this case is the yellow link, not the red link. And so the red link is kind of just there to transform the motion and to transfer the power. And all I really care about is I'm driving the green link, and I care about the motion of the yellow link. And so you can kind of just think about this system as the green link and the red link combined into this virtual 3-bar linkage. And again, that can be useful to think about as a linear actuator. And then that linear actuator is driving this other virtual 3-bar linkage that is the yellow link, the blue link, and this dotted blue line that you see. And that can be a much easier way to think about this particular scenario where the yellow link is the thing that you care about driving. In addition to, we mentioned earlier, like linkages can often replace power transmission components. When you're talking about, an unequal 4-bar linkages or an equal 4-bar, you can kind of visualize them like a belt and pulley reduction or a sprocket and chain reduction, same thing. And like I'm showing on the screen here, if my driven link is small and my driving link is large, then I have a kind of effective gear reduction where the input link is going to move a lot and the output link is not going to move very much. And the ratio of those two lengths acts roughly in the same way as the ratio of the diameters of pulleys or sprockets would. When you're talking about a 4-bar linkage, sometimes you have links that will pass through an intermediate state where they're lined up. Now, we talked about this a little bit when we were talking about indeterminate linkages. The key difference here is this can be very useful when one of those links is the driving link, because as long as one of those links is the driving link, the linkage doesn't become indeterminate. It's only when the passive link and the driven link line up that you have a problem. And so in this case, this can be useful and important. And when you're evaluating a system like this, it's important to understand that the directions of forces in your system change when you cross over this crossing point. So when you're on one side of it, your load will be producing a torque on your driven link or your driving link in one direction, and then once you cross over, that will reverse. And that's important. And also in this perfectly lined up state, generally speaking, the torque that you need on your driving link will become zero because it's in line, either in tension or in compression. And so this is useful when you're trying to do like over center locking, or you're trying to do like other applications where you've got like a small driving force at a very large load. All right, so we're going to talk about some examples from some 3005 robots from the past few years to look at how linkages and cams can be applied. So on our 2022 robot, we had this hook on our climbing system that would basically open and close. And so what we had is we had an air cylinder that formed a 3-bar linkage where we were using that 3-bar linkage to transform the linear motion of the air cylinder into a rotational motion of this little part here that is basically forming a bell crank. And then we had an additional 4-bar linkage. So this is a compound linkage, and the 4-bar linkage was kind of moving the power and kind of transforming this 60 degree rotation or so, maybe it was a little bit closer to 90, into an exact 90-degree rotation of the hook, and then it was performing this over center function to lock the hook in the closed position. Now, I already mentioned the kind of transforming linear to rotary. This locking function basically involves the whole linkage barely crossing over the kind of like aligned state that we talked about a couple slides ago. And essentially, this very, very slight passing through that aligned state to the other side means that, again, the force was reversed. So instead of where, closing the hook is kind of fighting the air cylinder, but when the robot weight is on the hook, the air cylinder is having to fight the robot weight, and it's not a very large air cylinder. It doesn't have a lot of force, so it can't really do that. But as long as you're over this center, now the robot weight is actually helping the air cylinder hold the linkage in this position because it's just barely crossed over. And because it's not very far over center, it doesn't take much force from the air cylinder to cross it back through, because the mechanical advantage gets to very extreme values when you're close to that aligned state. And so the key thing here is like you can see in this image here, we're able to open those hooks while the robot's hanging on it to kind of get off the other bar quickly, and that was the main motivation for this. Okay, so on our 2024 robot, we had a pretty large launcher, and that would launch the rings, the notes, and it had quite a bit of angle control on it. And when we would score in the amp, we wanted to deploy this mechanism with some rollers on it in front of the launcher to basically, the launcher would kind of get the note high enough that it could get scored in the amp, and then this diverter would kind of turn it around like almost 180 and launch it down into the amp. Because this whole system, already had a lot of motion on it, the motion of the launcher itself is used to actuate the diverter using a cam system, and then that is transferred using a linkage. And so there's this cam, which is just a standoff, and this kind of goes back to what I was saying earlier in the presentation about cams are not necessarily this complicated thing. In this case, it's basically just a bar on the robot. And then there's a follower, which is this kind of lever. Well, there's some animations on the next slides that are a little clearer, that actuate the diverter during the last 15 degrees of motion of the launcher. And then we have this 4-bar linkage, basically just to move this motion from the cam follower system down right at the pivot of the launcher out to the end of the launcher where the diverter is. This is a better kind of 3D animation showing that interaction between the follower lever and this standoff cam. The main reason for us to do this was to pull the mass of a motor and gearbox to drive the diverter off of the launcher. The launcher was already heavy. We wanted it to move quickly, and so putting a couple of pounds out at the end just to do this small motion on the diverter wasn't really going to be worth it. The robot also had a lot of motors on it already, and so getting rid of a motor was good for kind of like reducing the amount of failure points that we had. Especially since all of those wires to actuate that would have to go out on the launcher, so there'd be a lot of wires on this moving mechanism that we could avoid. Made maintainability easier just by having less components going out onto the launcher as well. Here's some slightly better animations here. We basically used a spraying of surgical tubing to kind of bias the diverter into a default out of the way state. And then the cam is essentially just pushing it into the deployed state. And this is how we make it so that it's only activated in the last 15 degrees of motion, is because when the follower is not touching the cam, the spring is just holding the diverter in place. There's a hard stop that keeps it in the right spot. And then we're kind of doing some power conversion here with this unequal 4-bar, where we're converting 15 degrees of motion of the driving link, which is the cam follower, and we're converting that to about 41 degrees out at the diverter. All right, and then kind of a similar system, but slightly more complicated on our 2025 robot. We added this later in the season, and so we redesigned our coral ejector after week 1 to kind of make our scoring cycle faster. If you saw our robot compete early in the season, or you've watched a reveal video, the robot has to do this really ugly, awful motion where it has to raise the elevator to get the coral off of clear of the ejector when it's scoring at the top level. So we were trying to get rid of that, and so we needed the ejector to kind of pivot between two orientations, because we needed to roll into a kind of a shallower angle to feed from the human player station, and then we needed to be more vertical to score on the top level. We were already very close on weight all season long, and so adding a motor in the gearbox to do this small actuation was not particularly worth it, especially since this was on the elevator on this horizontal laterator system that we had. There was going to be a giant run of wires out there, which was going to add even more weight. And also just kind of be a problem in terms of reliability and failure points. And it was going to add a bunch of moving mass to the elevator, which was also already very, very heavy, a lot of weight moving up and down. And so for all this reason, we wanted to actuate this mechanism off of the motion of the laterator that already existed. And this was, like I said, an addition we made in the season, so we kind of had to work around what was already there. And so this is a cam follower situation with a linkage to kind of move the power and transform it. We were not able to directly drive the ejector off of the cam. The geometry just didn't work in the packaging in the robot, so we had to have this linkage do the job. We spent a lot of time trying to figure out a direct just cam to ejector system, and we just couldn't make it work. And so we built this linkage, and it's just 3D printed parts. It's very small, very light. Saves a lot of weight out on the end just kind of doing this system. And basically, this is kind of the opposite of the 2024 situation where there's a larger motion of the cam follower, about 70 degrees, and that's resulting in about 34 degrees of ejector angle change. This is also a similar system to the kind of the 2024 robot where only the inwards most 4 inches of travel of the laterator is used to actuate the system. The whole thing is spring biased. And because the laterator extends in 200 milliseconds, this spring had to be pretty stiff to be able to snap this thing out in position, in a similar time scale to when the laterator extends. And the way that this geometry was going to work, that spring was going to be strong enough to kind of extend the laterator when there was no motor power. Like when the robot was sitting there before the match or whatever, the spring was going to be strong enough to kind of back drive the system because the laterator is very free moving, very low gear, very, very fast gear ratio. Is very easy to move. So we built this more complicated geometry into the cam follower where the cam follower is this little lever and it's interacting with a standoff it's got a spacer on it, but it's basically just a standoff similar to the 2024 robot. But as the cam kind of gets very to the end of its travel, it's got this little kind of a notch in the end, basically, where it barely starts to drop over the cam, and again, it reverses direction. And when that happens, it's similar to over-centering a linkage, where the forces in the system reverse, and the spring in the system actually starts helping the laterator retract rather than pushing the laterator into the extended position. And so it's able to kind of hold its position, in the retracted state passively. All right, we've got some time for questions.